So before everyone announces, after the meetup, whoever announces a job, go back to the pizza table right there. That way people can find you afterwards. All right? So, who is hiring and willing to wait at the pizza table after the meetup?
Jared?
Oh, first up, right here.
Yeah, we're hiring. We're always hiring.
Who is we?
Yeah. At AWS, we're hiring everything from data scientists, data engineers, big data people, and business development managers. Essentially what I do. We need to scale. So let me know if you're interested.
What was the company name again?
It's a bookstore that is trying to do a lot more.
All right, and they sell all sorts of consumer product goods, I understand. Yes, I see a hand up in the back. You need to shout. I'll try to bring the microphone around to people, but I might have to hard to give me feedback. We'll try. I don't think I have any other mics now.
Hello, I'm Will, from co-founder and CTO of Snowball Age. My personal background is research as a computational computer scientist at Columbia for about a year and a half now. For our startup, what we're doing is using AI and RL to basically help students navigate the SNS process. The student loan application process for SNS. So if you're a high school or something, you're trying to figure out how to pick the college, you basically text it, and we kind of interface like automated replies to humans throughout most of the conversations to basically help you get funding and find out how to get to college. So anyways, we're hiring for machine learning, data science, so also engineering. I guess.
All right, I saw E-Rob had it up. All right.
Hi everyone, I'm Rob, similar to spoke about last time. Data analyst at Etsy, and hired for data scientists. One for machine learning and AI, and one for neurovision graphics. We're really excited about quantitative insights. So this one person is the machine learning and AI, or computer science, take the data science, and quantitative insights take more data A, so really help with our hypothesis testing, time series analysis, etc. So yeah, go talk to me afterwards if you're interested.
And you get to work in Brooklyn. The cool part. So the whole borough.
Hey guys, my name is Troy. I'm a data scientist at Squarespace. We're hiring data scientists and data analysts. I will be sticking around for pizza afterwards, so just find me on LinkedIn. My name is Troy. If you're interested in Squarespace.
Hi, my name is Alan Just. I'm at Mount Sinai School of Medicine, so Upper East Side, the lunch in Central Park. I'm looking for an R programmer, data scientist. I'm going to work on environmental epidemiologic studies, understanding how air pollution and other kinds of pollutants impact children's health. So I'll be hanging out if that's interesting.
All right, we have another announcement over here.
Hey guys, my name is Laura. I work at Commonwealth Bank of Australia. We're recruiting business senior data scientists. I guess there is travel involved to Australia, obviously, Indonesia and South Africa. So find out about data.
We have Brooklyn and Australia. Anyone else? We know you can count on you.
Hi, I'm Sar. I'm the chief data scientist at VIA. You probably see our cars all around the city. We're hiring both data scientists and BI people. So if you're really, really good at visualization, apply for the BI job. We're here on the pizza table. And if you're the most brilliant data scientist you know, then come apply for the data science job.
And you have to be more brilliant than SAR. That's a tough part. Sets it high. That's a compliment. Anyone else? Last chance? All right, wonderful. Next up. The pizza this month is from Prince Street Pizza. So, I want everyone to take out their smartphones and go to bit.ly/pizzapoll, all lowercase, and rate the pizza. This is not a joke. We collect data. For those of you who haven't been here before, every month we get pizza from a different place, and sometimes we repeat places, and we collect data over time. And if you go to our website, I'll tell you in a second, you can see a bar chart of all the pizza ratings over time, generated with R, of course. So I'll give everyone else a chance, bit.ly/pizzapoll, to go vote. That website I was talking about, we have a new website. nyhackr.org. This was spurred because Meetup would no longer let anyone upload files to their site. We needed to upload presentations. So I just decided to build an entire website instead. Built it using R. And once you go there, you find the pizza pool there. You can find a listing of every single meetup we've had, including the presentation that's available and the video that's available. We also have a Slack channel. So when you're at nyhackr.org, you should go join the Slack team and have a conversation. We have chat rooms for getting hold of R, Python, Git, Stan, a few other languages. We have events, announcements. We have a job posting area. In fact, the Mount Sinai job was just posted on there today. So please check out nyhackr.org and sort of join the online community since we're here in person. After this meetup, we are going to try a different bar this time, one we used to go to a few years ago called AOA Bar and Grill. It is down West Broadway, just around Canal Street, I believe. It's a 4-minute walk. All right, only 4 minutes is all I'm asking of you. If you want to go to the bar, AOA Bar and Grill. All right? You'll be at the bar. Our speaker will be at the bar to ask any complicated questions. Bring chalk. If you want to attend Strata in September, it's coming up soon. We have a discount code. We just confirmed today. It's working. Someone messaged me it wasn't working. It is now. It is UGNYHackR20. UG, user group, NYHackR20. That'll get you a 20% discount on Strata. So go save some money. Our next meetup, we haven't exactly scheduled it yet. It's supposed to be, if the schedule works out, the Art Studio Roadshow. A few folks from Art Studio are going to come here and show off some of the cool new stuff they've been developing. So stay tuned. At some point, we are going to get that schedule locked down. So we covered jobs, the bar, the pizza pole, the website, Strata. Anyone else have any last minute things? With that, I present to you Don Mbanga talking about deep learning in general and in particular in R. So a big round of applause for Dan.
Oh, really? Well, thank you. I hope the presentation in the end is worth the applause. Right, so getting started. My name is Dan Mbanga. I do business development at Amazon Web Services. Essentially what I do my focus is on machine learning and deep learning engines. I work with customers of any size from startups to Fortune 100 that want to build and grow on top of AWS. So it varies from finding opportunities for them or optimizing whatever they do or finding new ways of doing what they do currently. I want to start this presentation by saying thank you. This usually gets left for the end of a presentation, but I want to begin by this because I appreciate the fact that you have a lot of emails in your mailbox and then you're spending this hour and a half with us today. So essentially what we're going to cover tonight is an introduction, a high-level understanding so that we get on the same page as far as deep learning is concerned, AI. And then the second thing I'm going to talk about is what we do at Amazon internally, how we leverage the opportunity of machine learning and deep learning and what we use these tools, these interesting new tools for. And the third thing that we're going to talk about is a library called Apache MXNET, which is an open source project, and I'm going to speak a lot more about. And it's essentially a deep learning library which has interesting features, and that's what we're going to cover. And one of the interesting features is that it supports R as a high-level interface. And the last thing we're going to do is we're going to dig into an example code of using MXNet and taking advantage of the opportunity of deep learning inside of the R infrastructure. Okay? Well, that's a good agenda. So to begin, I want to start by telling a story of what we call the flywheel of data, where we are. Technically, more and more data is being generated nowadays by virtually everyone and anyone. We're using mobile phones. We have our Fitbits that is generating data, mobile applications. There's data everywhere. There's a humongous amount of data being generated nowadays in the world. And better data gives you better analysis. So the more data you have, the more analysis you can get from that data set. And better analytics give you better product. When you get better product from better analytics, then you get more users, and more users generate more data, and then there goes the flywheel. So the way you get data generated nowadays is by clickstream, and then user activity on your website, on your web app, purchases, clicks, and then likes on social networks and other things like that. You also get better analytics from the tools that people leverage to do better analytics are things like object store, databases. Yeah, I think people are very much familiar with most of those. The Hadoop ecosystem was born about 4 to 5 years ago. A little story, I started off at Amazon as a big data operations manager, so I sort of built a support team in Cape Town, South Africa for big data. And so I remember back in those days, when you went on 2 or 3 different websites and you read about big data, you would have had 2 or 3 different definitions. It's almost the same thing now with AI and machine learning, where the hype is on, everyone is interested in it, but a few people can really define what it is. So the tools down here, as far as Hadoop, Spark, and Presto are, the new de facto standard that people are getting used to. And this is the new opportunity, right? The new opportunity is to use artificial intelligence and AI and data science and all these statistical learning tools to analyze data better and essentially get better product. And then better product is going to give you the opportunity to pinpoint your users, understand your users better, and essentially generate more data, and off you go with flywheel. Please feel free to interrupt me at any time if I have a question. I'm happy to keep this interactive as we go. Now, understanding artificial intelligence, just to make sure we're on the same line, like I said, you get multiple definitions if you go on multiple websites. The way we see it is that AI is sort of the umbrella term that encompasses everything, right? So it's a combination of learning algorithms plus hardware that essentially interfaces with the real world. When you deal with artificial intelligence, the thing that we're trying to replicate is the ability for humans to, or the ability for computers to emulate or simulate human systems, expert systems that humans do without really being able to break it down to a certain finite set of steps. If they ask you how you see, you know that you learn how to see, you know that you can see, but you can't really break it down. So how do you encode that into a computer? If they ask you how you speak, you know that as a child you learn how to speak, but how do you teach a computer how to speak? We converse, you can say things in certain words, but I will understand the meaning, I will understand what's on your mind. How do we make sure that a computer can get the intent of a person regardless of what word was saying? So these are the sort of opportunities that you get in AI. And so the way we see AI is an interaction between the real world and the computer, and then that to be as seamless as possible. So then you get applications like self-driving cars, playing games, and then automated turbine, or predictive maintenance, a number of things that really interact with the real world, but are driven by computers. And then machine learning is sort of the workforce or the workhorse for AI. As in AI, you need to identify patterns in data, and machine learning gives you the statistical background or the mathematical approach to essentially fit a certain function to the data. So in ML, the analogy that I use is that in AI, data is like the soil. And then in the soil, you plant a machine learning algorithm, and then grows out of it another machine learning algorithm, right? So you plant the learning algorithm into the data, and then you grow the other, the machine learning model that represents your data. And then, so machine learning is the maths part of it. I put this here to look a little smart, like I know what I'm talking about. And then so deep learning takes a subfield of machine learning that has to do with neural network. That traditionally, it's a very old concept back in the 30s and 40s. It was figured out already, but there was a challenge in terms of compute and data that we're going to get to talk about. But deep learning, this is prime time for deep learning because Moore's law is over. We figured out how to get compute way faster than the way the silicon and the CPU evolves. And then there's also a lot of data, like we talked about a little earlier, that gives us the opportunity to leverage that. And with GPU, deep learning can take neural networks to the next level and essentially give people the possibility to fit a network structure on top of data. So the opportunity that we're seeing now, the three main drivers for seizing the opportunity for AI machine learning are fast compute, where we figured out how to process data a lot faster with GPU. Ubiquitous data, where we figured out with social network and everything that comes around with it, how to essentially have a better knowledge representation of the world. And then advanced learning algorithms, where nowadays, because, again, leveraging computing data, we can generate more and more universal approximation functions. And every day there's a new paper, adversarial models, and, you know, multi-armed bandit, which is a new sexy. Like, there's a lot more new cool things that are coming out now in terms of advanced learning algorithms that give us the opportunity of artificial intelligence and AI and machine learning and deep learning. So this is a prime time for data scientists. This is a prime time for machine learning enthusiasts. And this is, yeah, it's a good time. So the way we leverage AI at Amazon is in a few ways. Search and discovery. Everything on the Amazon.com page is essentially driven by AI and machine learning and deep learning. The way we rank the product that we're going to present, the way we decide what asset we're going to present, the recommender systems. I used to tell the story, I buy espresso capsules on Amazon.com, and then essentially 2 days before I run out, I get a notification, do you want to buy it again? You know, so they sort of predict, you know, whenever I'm going to need a refill, and it's all driven by machine learning. In fulfillment and logistics, in our fulfillment centers, we don't have people running around, you know, picking up boxes and things like that. We have these 750 bins that we essentially throw things in them using a random storage mechanism, and we use computer vision to recognize whatever is within the bins, and then we have self-driving robots that pick them up and then move them around the fulfillment center and present that to people down at the end of the line, and then an agent can just pick up the item and verify the label and ship that out. Autonomous self-driving, they go around. When they run out of battery, they go and recharge themselves, and they come back and move around. It's really cool. I have a demo video that I can show later. And we have new categories for existing products, like essentially using optimization to make products better. Our goal is really to bring machine learning to everyone, and that AWS Amazon Web Services is the conduit for that. It's the way we want to extract that entire knowledge from Amazon.com and other business units and then present that to our customers in forms of platforms and services.
Move that microphone to the center of your shirt.
Is it better?
I can't hear you when you turn over your shoulder.
Like that?
Yeah.
Better? Okay, cool. So this was our first recommender system. It's the Amazon.com web page in 1997, 1998. Where essentially we had already personal notification services going around, and that was someone in the back end taking a list of what people bought, another list of what people bought, and doing the matching manually and say, hey, we should recommend this to that guy, and someone sending that notification. So the mindset was around for a long time, and then now we're just taking advantage of, you know, the tools and the automation platform to make it faster. This is another example of application of machine learning or AI at Amazon. If you use Amazon Video, if you pause a show or anything you're watching, there's this tool called X-Ray, which essentially pulls up in real time information about the actors within the scene at the exact scene where you hit pause. So the interesting thing here is that, as you can see, we're not using a naive facial detection mechanism. The actors are giving their back to the camera, but we're still able to recognize who they are, and then we give you more information about them, and then we can point you to some other movies that they've been in and things like that, all happening in real time. Of course, everyone is familiar with Echo. Who here is not familiar with Echo? Pretty much everyone. Okay, so the reason I like talking about Echo devices is that it's an interesting delivery mechanism, because I think part of the conversation within the next few months and almost a year is going to get into, you have a machine learning model, then what? So how do you scale that? How do you make it work in a non-internet connected environment? Or how do you make it work in a hybrid environment where you have the internet partially and then you don't have the internet anymore? So Echo really embodies that concept where you have a very, very small model running locally whose only job is to identify a wake-up word, right? When you say Alexa or Echo or Hey Siri or all these, you know, voice assistants, the only job of the model, which is very lightweight, running on the machine, is to identify the wake-up word, and once that is done, it opens up an MP3 streams, and then you stream in the command that is sent to the cloud, and then the rest of it is processed to the cloud, and the rest of the intelligence happens there. We have another device for people that like fashion. It's called the Echo Show, where this is the Echo Look, sorry. The Echo Show has a screen where essentially you can say, Alexa, take a picture of me. It's going to take a picture of you, and it's going to give you recommendations about what to wear. This type of jacket goes with that kind of jeans and whatnot. So people wanted to have a personal assistant, and so we made it happen for them. And it can get the history of the things that you've done in the past, that you wore in the past, and you could say, what should I wear today or tomorrow? And it will go, okay, you typically dress up that way, so you might want to wear this and that. So it makes some people laugh, it makes some people happy, so it's really happen. So these are a few examples, more examples of how we leverage deep learning and AI at AWS. For applied research, core research, Alexa, demand forecasting, pretty much everything is driven, every decision is driven by a model in the back end or accelerated by a model in the back end, right? Where natural language processing, understanding content recognition, dynamic asset generation, what are we going to present at what time, based on the customer's behavior on the page, all of these things are driven by AI. So this is a list of customers that currently leverage the AWS platform for artificial intelligence. Zillow is a good example where they do price estimate of houses on top of AWS. Netflix is an obvious one. NASA uses AI at AWS to give voice commands to the robots. And then there's a lot more. Pinterest, these are cool examples as well. Pinterest does visual search on top of AWS, where essentially you can start with a picture like that and then crop a lamp within the picture and do a visual search of the lamp and then come up with other images or pictures of lamp that are similar to that based on the picture. And then in beta, they have a Pinterest Lens, which is essentially an app. This is a model running on the phone where you can take a picture of an object or of someone on the way, and then it's going to search the space of pins and then show you other images that have similar pictures or objects. So a lot of momentum in the image recognition domain. And then Netflix uses AWS for personalized ranking, page generation, search, similarity analysis, the whole recommender systems. And then they had to scale in about 140 countries, essentially by porting the data, localizing the data a little more, and then analyzing that locally, and then generating the models, putting that in production that quick. So in the space of a bit more fun examples, this is called Neurostyle Transfer, where I bet you all have cameras that change the texture, the structure of a picture nowadays, and then those are variants of Neurostyle Transfer, where you can start with an image like this, and then you sort of overlay the image with a painting, and then after that you generate a completely, this is completely generated, right? Generated. So you can generate a completely new image that essentially replicates the model of this image and applies the style of the second image. So you rotate the pixels of the first image, and then you apply this style to generate this third stuff. So you might wonder, what the hell am I going to do with Neurostyle Transfer? This is a paper called Bringing Impression to Life with Neurostyle Transfer in ComSwing. Essentially, in this paper, they had an intro scene, and it was some form of horror movie. So from the intro scene, they wanted to apply the style of the painting that represented the horror movie, and then generated another video of the intro scene of a guy drowning using the style of the horror movie. So you can think about a few things you want to do with it. This particular paper got the collective machine learning and data science community to lose their collective mind, because the second author on this paper is Kristen Stewart, who is Bella in Twilight. So essentially, AI and machine learning is for everyone. You don't need to have a PhD or whatnot. Whatever people say is absolutely, not true. So the team that I work for is called Amazon AI, and essentially what we want to do is bring these capabilities, the knowledge or the experience that we have in form of platforms and services. And I'm not going to talk about all of this because this talk is not about that. But that was a long intro to actually, focusing on deep learning and MXNET, and that's what we're going to talk about a little later. So at the top layer, though, we have a lot of services, which is, pre-trained machine learning and deep learning models that we train, we scale in the back end, and we make available in front of an API. And remember when I was talking about these expert systems, how does a machine see, how does a machine speak? How does the machine interact with humans and understand the intent of a person? These are the kind of problems that we're trying to solve with these services, and we're trying to make sure that our customers don't have to do it themselves. So from a vision perspective, we have recognition. From a speech perspective, we have a text-to-speech solution called Polly. And then from a chatbot perspective, we have Lex, which is essentially the brain of Alexa that we took out and then we made available for people to build their own chatbots. And then underneath that layer, we have what we call the platforms, which is for people that have their own data that they want to train machine learning and deep learning models on, and not machine learning as of now. And they don't want to do the plumbing, right? They want to get started at a point where they can just start building models. Data scientists usually don't want to have to do with infrastructure. I don't care where you get the cluster from. I want to see Zeppelin. I want to see the Jupyter notebook. I want to see, the R interface. So it's kind of the problem that we're trying to solve there. We're doing DevOps for data scientists, right? And Amazon Machine Learning gives you an end-to-end way of uploading your data, training it, and then deploying that behind an API. As of now, it supports linear regression, logistic regression, and multi-class classification. If you want to get deeper into other models like tree-based models or support vector machines or other stuff, you can use Spark Machine Learning on top of AWS. And in terms of ingesting data for processing, or if you want to Dockerize your environment, you can use ECS or Kinesis or Batch. We can talk about that more later, but I'm not going to focus on that today. What I'm going to focus on is the deep learning opportunity. So under that layer, of course, we have infrastructure, we have GPU, CPU, and then we build stuff that run on IoT devices or mobile devices. But the area of interest here is the engines layer, where we pre-package environments and make them available for people to start building deep learning models. So with that, Jared and I actually had long conversations about what's the opportunity of deep learning for data scientists. Like, why would or should data scientists be interested in deep learning? And yeah.
But you also support Keras, I take it?
Yeah, so we have Keras, Caffe, pretty much all the popular. Yeah, so wherever you see TensorFlow nowadays and Theano, you probably have Keras, unless you really want to suffer, right? So I think Keras and TensorFlow, or Theano, or MXNet for that matter, because they all work together. People want to go into the high level library. Yeah.
Thank you.
This one?
The other one.
This one?
Further that way.
This way?
Yeah.
Okay.
Look over your right shoulder. It doesn't pick you up.
Like that?
Further.
Further? I
There you
have a mic assistant here. Okay, cool. Thank you, Jared. Yeah, so that's what we do. And so I think that the opportunity, so deep learning does essentially, I usually say that principal component analysis is one layer, deep learning or MLP. So it's about the opportunity of throwing more data and more compute at your problem, and then get potentially more accuracy. And we played around with a few models where we created a model with a neural network, and then we recreated the same, or tried to solve the same problem with random forest, or what else did we use? We use XGBoost. We use a few other methods to try and solve the same problem. Sometimes we had better accuracy, sometimes we had worse accuracy. But the whole thing here is that this layer gives you the opportunity to scale. It gives you the opportunity to do a lot more on a lot more data, and then to get potentially, hopefully, better and better and better accuracy. Something else that people are doing is that they're trying to use data set from other environments, like images. How do you make images as part of your data sources? Like, rather than using sensor and other kind of data, what if a picture is worth a thousand words? What if you use a neural network as a pre-processing stage and get some labels out of it, and use that label to those labels to augment the space of features that you use for a traditional support vector machine or random forest model? So that's the opportunity. And so deep learning gives you the opportunity to solve learning problems, where you can essentially get machines to actually learn without having to do hard-coded feature engineering. You don't have to prepare the data set manually yourself. You can just throw that at the model, and it's going to do some separation and let you know. You can do some language learning. You can, we have open source a library called Sockeye that essentially gets you to do neural machine translation. And that's one thing I like talking about, because if you could think about the way translation was done in the past, where you had to either use a word count, where you had to, start with a word and use the equivalent word in another language, or it improved and we started using ngram, where you use a combination of words and then you were translating that way, and then it improved and then people were using sentences and doing that. But in all of these cases, you sort of have to build a whole database of English and French version, which French is my first language, by the way, so I always use it as an example. You have to use a whole database of these, two entities and then do the mapping. And so it's hard work to maintain that. But nowadays, there's this concept called NMT, where if you think about the way I see or the way I get inputs in my system, my brain gets activated in a certain way. If I see you, my mind gets in a certain state. And because deep learning and neural networks are about replicating the state of the mind into the machine, the conceptual assumption is that as we get input into the system, what if we're capable of taking a snapshot of the brain activation? In the artificial world, that would be taking a snapshot of the active neurons and then port that to another deep neural network that is trained on doing another thing like speaking French with proper grammar, right? So instead of translating the words, you just ingest the words in English, take the active neurons, port that activation state into a French-speaking neural network and let it speak that thought or that, mind or whatever in French. So that's the kind of thing that we're trying to do nowadays. And I think we're going to converge towards getting a chip in my head, taking it out and putting it in your head, and you just be speaking. Anyway, so, and then perception is another way of getting the machines to see, solve problems, and reasoning. And so what we have nowadays is called the AWS Deep Learning Army. It's one-click. I'm going to give a short demo about that. One-click GPU deep learning machine image. So in AWS, we have this construct of a virtual machine called an army. We have pre-packaged, and we've tasked a number of our engineers to essentially prepare this machine for you to use, right? So they update that, and then every time there's a new version of TensorFlow, Keras, Caffe, and all these things, they make sure that the new version of the image is available. We have an Ubuntu version and an Amazon Linux version, which is essentially a derivative of CentOS. So the machine can go up to 40,000 CUDA cores, and NVIDIA just announced, or they announced in May, that they will release the Volta GPU chip, which is a beast, right? It has about 12x improvement on the current Pascal version of the GPU, and then we will be launch partners. So once the Volta comes out, we'll have that available on EC2. And then it has TensorFlow, MXNet, Caffe, and all these deep learning framework pre-computed, pre-packaged for GPU support and everything. Has Python 3, Python 2 as well, a bunch of notebooks example. And then you also have the possibility to launch a cluster of those using CloudFormation, which is a declarative language on the AWS environment to essentially spin up an infrastructure without having to hard code everything. So that's what we have now for people to get started. Now we're going to get into talking about Apache MXNet, like about the library. Who here is familiar with Apache MXNet? Few people. Okay, good. How about deep learning in general, TensorFlow, other libraries? Okay, a lot more. Perfect. So for those that are not familiar with deep learning or MXNet, essentially in deep learning you have to create neural networks, and for those you have to, and we're going to get through a process of solving a problem end to end with deep learning. But for those, you have to stack layers of what we call neurons that essentially get linear combinations of a certain input set. And then on those linear combinations, it randomly chooses a set of parameters. And then you stack these linear combinations up and up. And on each neuron, you have what we call an activation function, which usually has a threshold that will determine whether the neuron is going to get active or not. Remember when I was talking about the state of a brain, how do you activate the cells within the brain and things like that. So you start from that simple linear combination activation construct, and then the assumption is that you can stack that up and up and up in multiple layers and make some more complex stuff in order to get deeper into the input set you're trying to find paradigms for from a layered perspective. The simplest example is that if you want to do image recognition, if you want to recognize a person from a picture, the assumption is that you start with a set of pixels, and then you put that in a two-dimensional array, X and Y. And from the pixels, as you ingest them, the first layer will potentially identify a rough change in pixel. That could be your corner, right? If it's a picture of myself between my skin and my t-shirt, it will probably identify that there's a big change in pixel here. So it will start, like at the first layer, it will start constructing the difference between objects, right? The second layer potentially would identify the same pixel that is continuing, so that's a contour. So you can start from corners by identifying a rough change in pixels, and you can start reconstructing contours by essentially following the same object around, and you can bring it all the way up to identifying my t-shirt overall, or identifying my skin, or identifying myself, right? So the idea is that you have a layered approach at solving problems, and that's the benefit of deep neural networks. And at the top of the layer, let's say I want to build a neural net to identify myself in a picture, right? So I will ingest a number of pictures, and then I also ingest a label that in the end would say, this is Dan. And whomever the network identifies as you know, the person, there will be an error there. And then we go back into the machine learning world where you have an error function or an optimization function, and then you need to do gradient descent or every other type of, you know, optimization in order to minimize the error, right? So that's the whole concept. But because in deep neural network you do that in a staged manner, you have multiple layers of errors. You have multiple neurons that are responsible for the overall error at the end. How do you distribute the blame? Or how do you get every other neuron within the neural network to take responsibility for the overall error function, right? So there's this concept called the chain rule in derivatives, where you essentially propagate backwards and get the neurons to take responsibility and adjust the weights that come from the linear combination in each of them in order to get you the best configuration of the neural network that gives you the outcome that you want. So the reason I went through that whole history is that it's mathematically complex to encode all of that in a library. In the research world, a lot of people have been doing that manually, like writing the combination, the linear combination, building the layers manually, or deriving the error function manually back to back to back to back. So the benefit for these deep learning libraries is that they sort of automate a lot of these things for you. So all that, you just say, construct your network by declaratively telling me I want one layer, one layer, one layer, one layer, and then this is the kind of outcome that I want from it, and I'm going to take care of deriving the error, minimizing that. Just tell me how you want to optimize that. Tell me what the learning rate you want to have on that, and I'm going to take care of everything else. So that's the benefit. And so TensorFlow is one library, Caffe is another one, you have a few on CNTK, MXNet is another one that we back at AWS for a few reasons. So there were a lot of them in the industry by the time we sort of had to choose one, and we chose one to, which is called MXNet, and we sort of made it part of most of the products that we're building now. One of the main reasons we chose MXNet is that it's flexible. It has a mixed programming API where it supports many languages at the front end, right? So we don't want people to have to work with Java in order to use, the tool. We want data scientists to use R because that's what they like. And then so with R or C++, or like the backend is built in C++, but these are the binding languages. So at the top layer, you can build neural networks with any one of these languages. And then as you compile the code in order to run it, it all runs in C. So you don't lose in performance, you don't lose in anything, but you use an infrastructure or an interface that you're familiar with. It's also portable, where essentially you can build a neural network with Apache MXNet, and it's fully open source, by the way, so it's an Apache product. Amazon Web Services contributes about 46% of the code right now, but there's a number of other people in the industry and ecosystem that contribute too. So we have customers building models with MXNet, and then they run that on mobile devices, on drones, in browsers with JavaScript, and it's also highly scalable. The idea here is that when you start building models and you want to take advantage of a large data set, then you start falling into like in-core memory issues. Like there's just this much that the CPU can do or the GPU can do because it's memory bound, IO bound, and if you want to throw more data at it, you're going to have to scale out of the machine. And once you start scaling out of the machine, you start getting into cluster management issues, right? All the machines need to be in sync, they need to talk to each other, you need to, if you want to compute the gradients, you need to find out exactly what is the latest state. So all that state management is cumbersome. So MXNet gives you the possibility to almost linearly scaling. The state management issues make it worse for a few scalable libraries because that time managing a cluster consumes the overall time of your exercise. If you started with a job that was taking, I don't know, 8 hours on one machine, and then you wanted to, and you doubled the number of machines that you want, the assumption is that it's going to take 4 hours, right? It doesn't work that way because of cluster management and everything else, it's probably going to take 5 hours. So it's incredible that MXNet can scale like close to, I think it's at 88 to 91%, depending on the kind of network that you have now. So it gives you that near linear scalability across multiple devices and multiple GPUs and multiple machines. So a paradigm that we see is that some customers train models in the cloud using the GPU capability. They don't want to keep it in their environment because it's expensive, it's, you know, and all these things. And then once they have the model artifact, they can take the same copy of a model and then push that to an app that runs on you know, a web app. And they can also take the same model artifact and push that to the mobile. And then again, the reason I'm giving this background is that you can use R to build the model and then upload the model with another language and stuff like that. So this training and deployment is usually a challenge in production environments because the data scientist loves R, so she likes to just type her code in R, and then the production code runs in C, and then that's a 6-month exercise to do like requirement specifications or whatnot after you're done figuring out how to solve a problem to get that to go to production. So it's another reason why we like talking about that. So we have a number of people in the industry that are contributing to MXNet from Apple, MIT, Microsoft is doing a lot of work on that too. And that's the 88% scalability that I was talking about. So let's get a little technical into how you would process, or the workflow process as far as deep learning is concerned with MXNet. But before that, is there any question, comment? I'm actually just trying to drink, and you know, so if there's no questions, okay. I should have planted some questions. Like I have some friends in the room. I'll do that next time. Okay, so the typical process that you want to do when you want to process data, I mean with deep learning, is that you need to, I believe everyone here is familiar with, you know, vectorizing your data, right? Whether you start from an image data set or a text data set or, I don't know, any sorts of, you know, data set, you need to come up with a vector or a matrix or any form of deserialized version of that data set that you're going to pass to the model that you're creating. So we typically start in deep learning with tensors, and then a one-dimensional tensor is a vector, two-dimensional tensor is a matrix. You're familiar with that, 3D tensor. So this is what they look like. The API in MXNet that helps you do that, it's a wrapper on top of NumPy that essentially gets you to build NumPy arrays or NumPy matrices or NumPy tensors of higher and higher and higher ranks. And so that's what you get with mxnet.nd.array. And the next thing that you need to do after you've ingested the data in, you know, as a tensor is that you want to build a neural network in order to train your data, right? So there's a couple of ways you can do that, and MXNet supports both. One is what we call the declarative model, and the other one is the imperative model. And essentially, the idea here is that you want to build a computational graph. You want to give the library like being in a restaurant. You say, I want a pizza with this topping and that topping. You don't need to worry how it's made or done in the back end, but you declare that you want, you know, a certain configuration of your network, and that's what the MXNet.symbol API does. It gives you the possibility to construct what we call a computational graph by just describing the model that you want to build. And there's a few neural network architectures, from the perceptron, which is essentially a linear combination of inputs, and then to what we call the feed-forward networks, which we're going to walk through today, which is a stacked up, layered by layered, you know, linear combinations and activations, and to a number of other ones, and more complex ones like long short-term memories and other things like that for different use cases. So typically for image analysis, you have people that build what we call CNNs, convolutional neural networks, and I can get to talk about it a little more later if that's relevant. But the idea is that you start with an input layer, what I was talking about later, and then you have what we call hidden layers. These are the neurons that are contributing to learning stage by stage, step by step, the construction of your input data set. And then, so like I was saying, you can, from the first layer, learn what we call the edges by just observing co-located pixels and then trying to find out what's the difference between them. If there's a rough change, and you know sort of that there's an edge. And then by a combination of edges, you can start constructing intermediate objects or contours and finding out exactly following an object all around the picture. And all the way up to contributing all these learned stages into making a final object. And there's this concept called the output layer, which is a decision layer, or which is a prediction layer, or which is a classification layer. That's where you sort of say, okay, this is what I saw into this whole process. So moving data from the input layer to the output layer is called feed forward. And traditionally what happens is that you pass data forward, and then you get a prediction here. What is not visible here is that you also have a label, like this lady could be called, I don't know, Linda. And then so you would have sent the information out here that this is Linda, and based on the prediction that the neural network made, there will be an error, and then you would propagate the error back and give each neuron the responsibility over their contribution over the error. And then all these connections are called weights. So all these connections are actually what the deep neural network is doing, right? So your goal ultimately is to find the proper parameters for all these weights, and you can see there's a lot of them for just a 1, 2, 3 hidden layers network. So the more you grow your deep neural network, the more weights you get. Typical neural networks could have like up to 80 million or weights, and so that's really what is consuming time in processing data with deep learning. And so yeah, is there any question on that? No? Okay. So the next thing you want to do after you have figured out how to ingest your input data set, and and you've constructed ideally the type of neural networks that you want to construct for the type of problems that you want to solve, is that you have an optimization function, or you have an error function. And it usually looks like this, right? I'll put this whole long thing here to scare people out. I see like no one is, so you're like, yeah, I figured it out. Yeah, cool. Usually when I put this on, people are like, okay, so you usually have an error function or an optimization function of this sort with regularization term and all that you now want to minimize, right? Or you want to maximize depending on what kind of function you have. And so the goal is to derive that against each parameters that you picked up in these weights. So you minimize that error function against all these parameters, and you're trying to come up with a minimum possible. And it has this linear relationship because, again, the error is contributed as it goes. So you want to make sure that you can, as much as you can, process that in parallel. And I'm going to talk about how it's done from the hardware level. So this is obviously a bad configuration because, as with the number of GPUs and compute capability that you want to have, you want to have a kernel environment that can do all of these operations in parallel so that you can benefit from that. And so the MXNET module sort of does that for you. And the next thing after you've trained your models is that you have a certain number of parameters that impact or influence the way you learn. The goal is to get to the minimum. The minimum is a star right here of the error. And there's a few ways you can go about that. I believe you're familiar with the gradient descent or stochastic gradient descent. And then there's a momentum that gives you a step of how fast you go into finding your minimum. And then there are other optimization functions that are becoming more and more popular, like ADAM, ADAGRAD, or ADADelta, which are just variants on the gradient descent, and also take advantage of many batches. Because the idea is that if you do the stochastic gradient descent is a lot more accurate, but the challenge there is that it's computing the gradient on every single observation and trying to optimize the gradient on every single observation. But you can take 10 observations at a time and then compute a gradient, and you're going to have an error that is not too far from a gradient that is not too far from what you would have had if you had if you had computed on every single observation, but you would have had saved 9x the time that you would have spent if you had gone on each observation training and all that. So there's a few ways to make that happen faster, and that's where machine learning and deep learning jumps into the art part of the house, right? Where the science piece is figured out, but how do you find these optimized parameters? The initializers is the initial value that you're going to give to your connections, your weights, your neural networks. The optimizer is which one of these are you going to choose, and then the learning rate scheduler is how do you want your learning rate to change over time. You could say that after this much iteration, be more aggressive or be less aggressive. Initially make big steps, and then once you start converging towards the minimum, start making smaller steps because you don't want to jump over the minimum and then start doing other stuff. So there's a few things you can do in order to optimize here. And that gives you some opportunities. And you also have a few, I put this here to sort of talk about the vanishing gradient problem, where if your error becomes smaller and smaller and smaller over time, the derivative is sort of going to plateau to a zero asymptote, and then you're essentially not going to optimize anymore. So again, these parameters in the MXNet libraries give you the opportunity to essentially set the hyperparameters and get your network to minimize or to converge to the minimum faster. There's more that is happening in the industry where you can essentially outsource this responsibility to a third-party system that is going to use Bayesian optimization to find the proper hyperparameters faster for you. I said Bayesian optimization is happy. That's the kind of things. So you get your input data set, you create your tensors out of it, you create your neural network structure based on the problem you want to solve, and then you train that neural network on your hardware, GPU and whatnot, and then you optimize the parameters that you want to apply to your neural network. The next thing you want to do is to scale it. So the typical process for training deep learning networks is that if you had just a single machine, you start with this initial data set, right? So you have this data set and then you split it because you want to distribute that. You have 4 GPUs in your machine. So you start by splitting your data set from an input perspective, and so you read the data partitions, and that means you vectorize that, you create all the things that we talked about earlier. And after that, so you have a key value store that is external to all these things, and you need to pull these parameters, the thetas, or I didn't call them thetas, but all these connections, all these weights that are going through the neurons within your deep neural network architecture. So you sort of need to pull down the state from a consistent view for the whole machine. After you pull down the states, you compute the gradients, right? So you find the error, and then you minimize the error within the different GPUs within the machine. And then every GPU is probably hosting a copy of the model, of a section of the model. So they all compute things locally, and then they send the gradient back to the key value store, which is external to the cluster, right? And then after that, you update the weights within the cluster based on the error. So that's the whole process. It's that you have connections, you make an error, you pull these connections, you compute a gradient, you minimize it, and then you update the weights, and then you go on and on and on again, multiple iterations until you converge to a point where you're satisfied with your error, and then you've trained a deep neural network. So if you want to move from this configuration of single machine to having multiple machines that are working separately, because MXNet uses an external key value store, you essentially have no change in your code. So instead of, and this is a big problem, like if you're familiar with multiple parallel processing type of compute, or MPI, I was talking to some people that were doing parallel processing back in the 90s, and then they walked me through the pain that they had. I'm so happy that I wasn't there then, because they had to write all the parallelism code, and they had to make machines talk to each other manually. I see he's nodding, so he probably knows something about it. So yeah, all of these things, and then so one of the key challenges for these new deep learning libraries is to make it possible for people to move from one single machine, single GPU, or multiple GPU processing to multiple machines in a cluster, multiple GPU and all that, and then you just don't change your code, right? You just send it, and then the framework takes care of it. So that's that. And then the last thing from a technical perspective that you need to look at is, how do you input the data? So there's an I/O library that essentially makes it possible for you to ingest data. There's no picture here. So you can start with the MXNet, the I/O, and then create your own iterator for your data ingestion. Or you can use a record I/O to ingest record data or voice data. Or you can use MXNet, the image, to ingest images. So we've sort of walked through the iterator for you, and you just have to use it. So I'm going to quickly go through, because I have to show you a demo, but I'm going to quickly go through how you can get started on the AWS environment with everything that I just talked about, and it's just some 5 or 6 slides about that. So the first thing is that you need to ingest data. I believe you're familiar with that. So you either upload data or you use Kinesis for a real-time data set for production, but you should never underestimate the bandwidth of a FedEx truck. So we have these AWS Snowball Edge that essentially gives you 100 terabytes data transport capability with onboard compute, has a couple of Kindles on it, a Kindle at the top for the label, and a Kindle on the side for manipulating that, cables and everything. You plug it to your environment, and then you push it to the cloud. Customers love Snowball Edge, so this is a fun pick where they always take selfies with the Snowball, when they have it, and then they ship it back to us. So if you use Snowball, send us your pictures, and my next presentation will have your picture in it. And then if you have a bigger requirement, well, we have the Snow Mobile, which essentially gives you 200 petabyte capability. And then our customers fight for sitting next to the driver, like, I want to drive it, I want to drive it. So it takes about 6 weeks to load, and then 6 weeks to unload. We give it with full security, 24/7 and all that. And these are the racks in there, right? So it's like a whole data center move. So, and after you've ingested the data, well, you have multiple data stores and data sources for multiple workloads, S3, Glacier, Aurora for relational database services and all that. And after that, you have a whole family of compute capabilities, right? From EC2 to Lambda, which is our event-based processing compute. And then for EMR, which is Elastic MapReduce, where you can have essentially big data, the Hadoop ecosystem automated, and the ability to launch a Spark cluster of 1,000 machines if you want, auto-scale it up and down for security and a lot of other features. I love it because I used to work there. And then like right away, or Redshift, which is a BI database, and Athena, which allows you to query data straight from the data source without having to have a cluster running, serverless data processing, and QuickSight, which is for data visualization, and Amazon AI, which is I haven't spoken about everything, but it's the family of product that gives you the capability to do AI processing. And to wrap it all around, we have Amazon Glue, which is essentially an ETL solution that helps you create pipelines of end-to-end processing of your data set, right? And Mechanical Turk has a tagline of artificial intelligence, where you have a job that requires human intelligence, like recognizing specific objects within an image, and you can create a job, send that to people, and then they create the ground truth data set that you use for your machine learning job. And then security is the top priority, it's the most important thing, so we wrapped everything else within the AWS security environments. So jumping on R, which is the other important factor of the talk today. So who here is not familiar with R? No one, so I can just stop here, right? Great, so R came from the Bell Labs, and then it was created by John Chambers in 1976. I'm trying not to mess up here because he gives me lessons about R all the time, so I'm watching I'm standing next to R for everyone, so I'm watching my mouth here. And so John Chambers created S, the language S, which became pretty popular in the 70s, and then back in 1993, a couple of guys, Robert Gentleman and Rossi Haka, in the University of Auckland, created the R language. And so R is pretty cool. I use it a lot when I want to benchmark a certain algorithm, or when I want to essentially solve a problem, because I think it's one of the most mature machine learning libraries out there. It gives you the possibility to solve a lot of problems almost automatically. I remember when, for example, if you were using scikit-learn and a number of other tools to do cross-validation or grid search or a number of things, it's one-line command in R, and then you have to code like 15 lines in other languages. So it's really a quick step into solving a problem, at least benchmarking what you want to solve. So it gives you the possibility to do interesting things like plotting probability functions and just statistics in general. And with some nice graphics. The other thing is that you can, do some traditional machine learning, like fit functions, with R. And this is a simple example of, a linear regression where you can predict the sun's height based on having the farthest height. As you can see, it's very, it's not really finding any pattern, but anyway. And then you can also have, you know, hierarchical clustering with like building dendrograms and the backbone behind random forest and all that, where you can use OurOne command and you dig deeper into a data set. And next thing that you can do is that you can have nice plottings and nice graphics, you know, built from R. And this is very, very important for the data science process because it's very iterative. There's a good quote about, you know, data science. Well, there are two quotes that I like. One is that data scientists spend 80% of their time. Who can finish that? And 20% of their time complaining about cleaning the data. Yeah, so it's a very iterative and painful process. The other fun quote is that you need to torture the data long enough for it to start telling you the truth. So once you have data, you really need to look at it there, you know, and then sort of process that for a long time. So that's the opportunity with R. It gives you a very, very easy way to do that. And now the claim that, you know, we're making is that you can also use R for building deep neural networks, right? So you can do it. MXNET is available. You can just upload the libraries like library MXNET like everything else. I have sample code to install it. It's lightweight. You can run it on your computer, or you can run it in the cloud, or you can run it, I don't know, in multiple environments, and then essentially build your deep neural network and then benchmark that. So with that, how much time do we have, Jared? We're good on time, right?
15, 20, 30.
15? Okay. So with that, we're going to move to the code walkthrough where I'm going to show you how to essentially solve a problem or with MXNET. And I have it here. So the first thing I'm going to show you is how to, who here has an AWS account? Almost everyone. I appreciate your business. Who here doesn't have an AWS account? I'm just playing. So when you get on the AWS infrastructure, you know, we high level, you know, we sort of trying to solve the IT and automation and like a few problems that people are facing when they're building intelligent systems or when they're building systems in general. So it's a long story, but essentially some cool quotes is that every developer has an average of about 3 new features a day, you know, when they use AWS, right? So there's a lot of features. We have about 90 plus products and services now, from anything from compute to storage to Internet of Things to contact centers now, game development, mobile hub, and applications, like pretty much everything, and analytics and artificial intelligence nowadays, right? So this is where I spend most of my time. But in my first couple of years at AWS, I was working here mostly. Like my team was supporting these products. And then for data migration, virtual private, you know, clouds where you can have a whole virtual data center on top of the AWS environment and BI. So there's a lot going on AWS environment. So what's interesting for us is EC2. EC2 is where you can have virtual machines, you know, as a service, where you can essentially launch a machine and then it's pre-configured, or you can configure it all yourself. So when you go to launch an instance, you have a few choices there, from Ubuntu, Amazon Linux, and then a few other choices here. You could also have your own custom machine image. As you can see, I have a deep learning army, including R package, because I installed it. I recompiled the environment with R myself, and I can share that code with you. I used to give a class on IoT, and then that's a bootcamp client machine for the IoT. And I have this machine now that I call Eigen Machine Learning, which is my default data science box. But we also have this AWS marketplace where you have pre-packaged and pre-configured machines that have essentially a bunch of you know, software already pre-installed. I think we have about 36 categories now, and more than 36 or 38,000 products. I don't keep track anymore, but it's a lot of them in multiple families, from e-commerce, education, financial services, and whatnot, and so all of that. So the idea here is that a machine will be pre-configured, pre-packaged, and you can just launch it and use the software that sits on top of it. Many people that put machines on the marketplace charge for it. Sorry. But the deep learning army, which is the machine that we build and maintain, we don't charge an extra for it. So if you go up there and search for AWS Deep Learning Army, you have a few choices, right? You have the Deep Learning Army with Amazon Linux version, which is the CentOS, derived version. And you have the Deep Learning Army Ubuntu version if you're an Ubuntu person. And so you can just select the machine here, and you have the configuration. So you will pay for the machine you launch the Deep Learning Army on. And as you can see, the software is 0, so we don't charge for it, but we charge you for EC2. And if you say continue, then you've selected the machine image that you want, and then you need to select the hardware you want to run the machine on. We have a few machine types here. In the GPU family, you can say, we also have FPGA, which I think is a bit crazy for people that are interested in it. But if you say GPU instances, and then so these are the G2 family of instances, GPU, which we started launching in 2013, and then people are using that for image processing or game processing and all these things. But if you select GPU compute, you have the P2 instance families that have a lot more GPU capability. For example, if I select the P2 8 extra large, I believe it has 8 GPU chips in it, and 16 extra large has 16 GPUs in it. So that's the one that gives you about 40,000 CUDA cores. And I go to the configuration of the storage, and I select all the parameters. I add storage to the machine. I say I want 500 gigs of disk attached to the machine. I say I want to tag it if I want to or not. I want to configure a security group. The security groups are essentially wrappers around the machine, right? It's like a firewall that sits with the machine. Do I want to open this port or not? Like in this case, the port 22 is open, and I can decide to open it to just my IP, this current IP or not. But anyway, these are EC2 features, and then I launch it, right? And I select a key pair that I want to use to SSH into the box. I acknowledge that I've selected that key pair, and I launch the machine. So it's as easy as that. So that's the first part of the demo. Like with this machine, launch failed for whatever reason. This is where you promise that the demo was working before. Like I swear it was working before. So yeah, so I only have a limit of 1. I can go and then, so because I already have a P2 running, and that's the cool thing actually. I'm going to act like I planned this. So at AWS we have the concept of launch limits, because it's very easy to launch like hundreds and thousands of machines. So we apply default limits to the number of machines you can launch, so that people fall into this, and then they actually call us, or they go through their admin in their companies and say, I need more, and then it's a very specific process. It's like, I want more machine, and then we can increase your limits, and then you can launch more. So yeah, I can only have a few P2s, and I already have 1 running, so I'm going to cancel this launch. And then so after you launched it, it looks like this. And then this is a P2 that I have running right now, right? Where it essentially, you have access to a public DNS for your machine, where you can just go on the interface. And so I have a bootstrap script on this machine. I can actually show it to you. Where is the user data? I forgot where to find that. Instances. Oh, I can do this. Instance settings, view changes. Oh, it's not here. Anyway, I'll show the script. So when I start, so I have this script that essentially, I don't know if you can see it. I don't know how to zoom this, but I can share it. So essentially what I do here is that after I launch my machine, and there's a way you can push that to the machine when once it's up, you can run a certain number. You can essentially run a bash script on top of it. So what I do here is that after I create the machine, I install some libraries that I like using, a bunch of things like tmux, htop, and whatnot. And then I install RStudio, and then RStudio server in order to access R via browser. I have a few R scripts that I like, apply predictive modeling, the examples. So if you have that book, this is pretty cool. You probably recognize most of these packages. And then I do install, what is that, Shiny server to serve R, and you see the password of my instance there. And then I add a lot of things. So I install MXNET essentially by recompiling the R package for MXNET, because the current version of our deep learning army hasn't compiled it with the R package, but it's very easy. It's essentially this much, scripting, and then I have R support within the GPU-enabled machine running on the cloud, and what I can do is that I can just go on RStudio afterwards, and then I have this whole interface, right, with Shiny and all these things. So that's the idea. The idea is that if you want to benefit from the potential of the cloud, you start the machine like that, you run this bootstrap script, and then now you have access to R running in the cloud with GPU support and enough capacity as you want. So that's the whole workflow. So another thing, the way the machine looks in the back end is like this, right? So after you get a machine, what I do here is that I can SSH into the box. And when I get into the box, can everybody see correctly? Right? So when I get into the box, I added some stuff there, but I have this source package that has everything pre-installed, like pre-configured. So we added everything from deep learning, the most popular deep learning libraries, Caffe, Anaconda 2 and 3. So we can also do the traditional, scikit-learn and everything else you would want to do there. Have TensorFlow, which is very popular. And then we did something else in compiling linear algebra, acceleration libraries like OpenBlast, basically in algebra subsystems, and other ones. We have the Intel math kernel acceleration also library there, pre-configured and installed. We tried to go through the pain of doing that manually, and then it's a headache. So you have it there, just use it. And then you could either go to MXNet here and then get into some examples, so you have the whole source code here, and you have a bunch of examples there, right? For, there's not enough time to show you everything, but you have some fancy stuff like autoencoder or adversary examples. So who here is familiar with GAN, like generative adversarial networks, where you're trying to trick a network by getting a discriminator, and then I forgot how the other one is called. But anyway, so we have examples there. Style transfer I talked about, a bunch of IPython notebooks, and there also are examples there, so you can just go ahead and use that. So going back to the front end, so what I've done is that I installed the machine, I installed RStudio Server, Shiny, and everything, and it gives me this interface where I can write my code. Right now, getting into the code for the last 10 minutes that we have, the code is actually available online on Jared's website. We gave a webinar about a couple of months ago where we walked people through this. So we made a decision to go through a code walkthrough instead of going to a live demo, because you never know what can happen. So essentially, the process here is that we upload some R packages for doing a few things like pre-processing data and doing some useful stuff. And we had XGBoost there too, because we wanted to compare some accuracies. But it's a very, very simple, small data set, simple network model that we created. We have data, we created a feed-forward network. Remember what I talked about, we pass data through. We have a number of helper functions, so it's all there on the right side. So we ingest all these packages. So you're familiar with this, I'll skip that. The data set that we had is the New York City planning data set that essentially gives you the valuation of certain houses and accommodation in different districts of New York. So the traditional process here is that we read the CSV data set and then we validate some of that data set. So we read the training and test and validation data set. So it's the same approach that you have with the traditional machine learning, where you have your training and then test data set, but the deep learning ecosystem adds the validation step where you train it, you validate it, and then you test it. It's just an extra step in validation. So what we do here is that we take out the features that we want to use for training. And again, this is just a demo, but you can go with it at scale and you leave everything in there if you want. The idea is that you don't have to babysit the data set, because the act of minimizing the error function is going to select, it's going to do regularization for you, and a certain number of things that you have to explicitly give to the network, to the model. So we select a few variables like the total value, the borough, the school district, council, a few things about the data set. And we do the same for validation and test data set. So after that, we look at the data set a little bit. So we see that it's pretty normal, our stuff. And then we take a list of the data, and then here we just want to plot the data to have like a distribution if we have issues with like class imbalance or whatnot. And I believe at a point here, what are we doing here, Jared? Like high 500? Yeah, class balances. So that's exactly what we're doing. So we're trying to find out what is the class balance on the data set. And so the response that we want to have, or the target, whatever we want to predict, is whether it's high or not, or the value is high or not based on the threshold that we set. And so we get the variable names, and all of this is normal. This is data pre-processing that you would have done. We're just preparing our entire data set for processing. No deep neural networks happening yet. The next thing that we're doing is that we use the vtreat package that essentially does feature engineering for you. You can do design treatment C to essentially, it runs a certain number of data pre-processing libraries or code on top of your data set in order to come up with a final version of like removing variants, non-variant data set, or treating outliers, or treating a certain number of things about your data set. So it does that for you by default, and that's why I like R, because it just does it for you. And then you can prepare your data set for after treatment. You create matrices off of your data set for your training set and then the outcome. Same thing for the validation set and the outcome, and then the test set and the outcome. And then you're essentially putting that in sparse models so that you don't use all the space on the disk with 0 values. So again, this is pre-processing. So where we are now is where the deep learning or the MXNet part begins. The library is extensible enough for you to come up with a custom error metric. And in this case, it didn't support the log loss, the multivariate log loss, and then we created a custom metric that we attached to the mx.metric.custom in order to essentially have a multivariate log loss function, which essentially does the log loss on top of the error function that you want to have. And this is where we construct the neural network. So it is as simple as having the symbol API that I talked about, where you're constructing the dynamic graph or the computational graph of your model. You start by creating a variable. The variable is a placeholder that represents the data set that you want to pass into the model. So after creating the variable, the next thing that we do is we do a dropout. A dropout is essentially, the idea of dropout is that because neural networks learn by you passing data through the model, the idea is that if you drop a certain percentage of the models as you pass the first iteration of the data, and you randomly drop another percentage of the neurons in the model, the network is going to be forced to learn because it doesn't have the same neurons involved in the processing at all time. So that's why we randomly drop, in this case, 20% of the neurons that will participate in the learning process. And then after that, we do a fully connected. The fully connected layers are what we saw before, where you have every neurons in a certain layer participating, receiving inputs from every neurons from the layer before, that being the input layer or an intermediate layer. So and when you say number of hidden here is 256, we're essentially saying that we want to have a fully connected layer which has 256 output neurons, which has 256 neurons. And then we do batch normalization, which is normalization as you know it, right? For every batch, we normalize, the data set in order to not have crazy behaviors. And after that, we do activation. So again, activation is the whole concept of after linear combination, you activate it. That's where you replicate the behavior of the brain. And in this case, we use the ReLU. There's a few functions that exist in the activation world. You can use sigmoid, which is what a lot of people are familiar with. And ReLU essentially makes activation or derivation faster because the function is f of x is equal to x if x is greater than 0, or is equal to 0 if x is less than 0. So to derive f of x is just 1, and if it's less than 0, it's 0. So derivatives run faster, and it was not proven to be less accurate than the other complex functions, and that's why we use ReLU. Then we do dropout again, which we're familiar with, and then the pipes here are essentially a ways to chain that. Again, we're building a graph, so we're just passing instructions from layer to layer, and we do another fully connected layer of 128. So we started with 256 down to 128. Another normalization, another activation, another dropout. Now at this point, we are ready to make a prediction on the outcome that we want to get, right? The outcome is whether the price, the value of the property is high or not. So it's a logistic regression. And then for that, we have a fully connected layer with one single, hidden neuron, which is going to have one neuron that we attach to one logistic regression output layer, right? So that's the essential construct of a deep neural network. So you start with an input data set, you build fully connected layers, and then the idea is that you go from high to low, 256, 128, down to one output layer where you force every linear combination to go down into 1. And then after that, you activate, you apply your logistic regression output there, which means that you put the logic on top of that, and you get the probability of, if it's under 0, if it's below 0.5, it's low. If it's higher than 0.5, it says high. So we've created we've constructed the deep neural network, but we haven't done anything with it yet. And so that's what we do here. Here we just type net, and then we see that it's a C++ object. Again, we wrote, yeah, quick question.
Sorry, so when you specify the layer, do you add the bias?
No, you don't. Yeah, we don't need to. It's inbuilt by default. It just takes care of it. Yeah, we don't do that explicitly here. I know what you mean. So the bias is the extra. You can encode that if you want. But when you construct the layers this way, we don't need to do that. So the framework is going to take care of that. Because in the end, the bias is going to be optimized as well. If you want to create a specific, if you want to add a specific neuron that will contribute in the bias, you can encode that yourself using the imperative, aspect of MXNET. But we don't do that in this case. Okay. So after you've created it, the neural net object has a certain number of arguments where it has the data variable that we talked about earlier. It has the definitions of the different, like you see here, you see the weight. Back to your question, my friend, you see the weight and the bias there. So we didn't have to specify it, but it was created by default. That's what I meant. So we add that. You could add it if you want, but we add it. And then we have this library called GraphViz that can help you visualize your network, right? So it gives you a good insight into what you've been doing. Oops, sorry. Where you can have a good plot that say, okay, I get the data and I drop it out, I get fully connected layers, normalize it, activate it, and off you go, and off you go. And this is really the simplest construct of deep neural network, and you will see it everywhere in many implementations. Most complex networks take a small structure like that and then start stacking them up like Lego blocks to build more complicated stuff. So after that, we want to train the network. So in this case, we did that on Jared's laptop. So we added CPU threads. We forced it to work with CPUs. And then MXNet has a seed function to essentially force reproducibility in your code to come up, because you randomize at a point. We want to make sure that every time you run the code, you generate the same random values, so that if I share my code, you can come up to the same result. And so at this point, we set the seed to this. We set the environment to use 4 threads of a CPU. And then we use the MXNet.model.feedforward library to essentially bind the network structure that we created to the data set that we have created in matrices and iterators. And that's what we do here. So the symbol is a computational graph of the network that we created. And then the X is the training data, the Y is the outcome of the training data set. The optimizer, remember when I was talking about the optimizer, the evaluation data, And then the context, this is the interesting part. The context is where you want to run the code. So if you want to move from CPU to GPU, it is as easy as mx.gpu or mx.cpu. If you want to run on 10 GPUs, if you have 10 GPUs, it is as easy as a list of mx.all GPUs that you have. If you have multiple machines, you have to specify a key value store, which is external to these machines. So you choose one machine to host the key value store, and then you point every other machines there, and it's going to do all the processing that we talked about. And then you show the evaluation metric, which is the multi-class log loss that we spoke about earlier. You tell it how many times you want it to, pass the data through the network. And this is important because we use dropout. And remember, dropout randomly chooses a certain percentage of a data set it wants to drop, of the neurons it wants to drop, and you use it that way. With a batch size for the multi-batch, gradient computation, and that's just the structure of how the data is within the row major, major. And that's that. So after you run that, it runs for a while, it trains, you're familiar with the training process. And after that, we construct a prediction function, and then we use the normal predict function to essentially pass new observation to the model that we created. With a certain layout, and then after that we look at accuracy. So what we started doing after that is train the same neural network with a few other traditional ways that we're familiar with, like with an ElasticNet model from GLMNet. It's as easy as that. It takes less steps, but the claim that what we wanted to achieve is that deep learning is better. But for this data set, things are actually very, very, very common. You get to the error. The margin is not that large, but we wanted to compare. So here we're exploring. So the whole demo is over here because you can train models and you can predict. But then we did a little bit of ElasticNet, and then we also had predictions saved into an object. Yeah.
Maybe I missed it. Did you specify an initializer?
Oh, did we specify an initializer? If we don't specify an initializer, it's going to take the default, which is a Gaussian, the normal distribution. So it's just going to throw Gaussian distributions at it. Okay, that's a good question. Yeah. So, and there's a few other initializers. There's another one called Xavier, and then other ones, yeah. So we did that here, and then we also trained an XGBoost model on top of that. XGBoost was hard to beat, right? Because it's fast, it's accurate. I think it was the best performing model on this data set. But I'm proud that the MXNET team is also the team that created XGBoost. So that was my argument when it came out. Jared was like, XGBoost is better. I was like, it's the same team. So, and then so we also had predictions, and we also did something with support vector machines in order to compare. So the whole thing is about comparing. And then we plot the ROCs for all of these models, and then this is the performance here, right, where XGBoost is like really, really hard to beat. It converges really fast. The area under the curve is much larger. But I can see the margin is not that large, and then it's very small data set. But yeah, so the net is there, and then so the neural network is actually, well, over time it does, sort of better, but it's arguably so. These are within a very, very small standard deviation. I think, what did we say when we were presenting on the rule? Like, as you can see, these are all doing very well, and they're all performing almost equally. So the goal wasn't really to compare. We wanted to have something visual, but the goal was to show the process of constructing a neural network as easy as that, visualizing that in an R interface that you spun up from this infrastructure. So with that, that's the end of the demo. I'll take questions and or comments. Also go back to the presentation and then share my contact in case you want to reach out. Happy to talk to you. That's my email. Shoot me an email if you have. Yeah.
So when you train your model, how do you pick those parameters?
Yeah, how do I pick so the question is, when you train the models, how do you pick the parameters? Which parameters are you talking about? Is it the
number of nodes, usually the GDM, like the steps.
Yeah, so that's sort of where the art part of neural networks is coming in. If it's about the network structure, what people do is that for the problem they're trying to solve, they usually start with something that already works. And there are some very popular networks out there, like the VGGNet, like the ResNet and all that. So if you have an image, recognition problem. You can start with that. And there's this concept called transfer learning. And then no one can really clearly explain to you why they chose this much layer and did that much stuff. But the idea is that they work. And it was done almost experimentally, and then with a lot of trial and errors. But it works as of now. So you can start with that. And then transfer learning is about cutting off the top layer, the output layer of these models, and then adding your own models. For example, if it's a model that was trained on recognizing 1 million people, you can only train that on recognizing you and your friend. So
as a follow-up on that, I'm curious, like, so if you know certain structure works for, so if you know like a certain structure works for image processing or path recognition, those kind of stuff, but given you know that, how do you go about it? Choose the maximum model.
right. So there are some guidelines. Like if you have an image processing, that's where you go down to understanding the structure of different networks. If you have an image processing problem, you probably want to work with convolutional neural networks because the structure is about, like running a filter on top of an image and then coming up with image structures. If you have a data set that has a temporal dependency, that's where recurrent neural networks are very popular, right? Or recursive neural networks if you have some special relationship between objects within your networks. So there are a number of papers out there, a number of canonical networks that sort of give you intuition and guideline. Unfortunately, you sort of have to read them all, and then, not all, but at least a few of them, and get familiar with what would sort of fit your problem space. But typically, your problem space would lie in a text data set, or text processing, or image processing, or video or audio processing. So these top level problems would guide you towards a certain set of neural network constructs or cell types. And then you can start getting into more complex cell types like LSTMs or GRUs, or there's a lot more fancy ones that people are creating every day. But the way I would go about it is that I'll start with a simple one that fits the problem space that I'm trying to resolve. Probably reuse a model that exists already. Or take that network structure and then sort of try to improve on that.
Anyone else? All right, if there's no other questions, you can ask questions in that bar. Last chance. All right.
Here.
Front.
So I tried running that code, and MXNET isn't on CRAN.
Yeah.
So you get to download the package and install it. I'm wondering if you could add your notes on how to do that on your
Right. We could do that.
The question was that MXNET is not on CRAN. You need to install from a different repo using the drat package.
Right.
So we'll add that into the notes so people can see that. All right. So everyone, big round of applause for Dan.
Thank you.